Hello, I'm going to talk to you about minimum sum of squares clustering with site constraints. This is joint work with Benedetto Manca at the Università di Cagliari in Italy. So the problem I'm going to talk about is the MSSC, minimum sum of squares clustering, and it's also known as the k-means problem. So given a bunch of points in our M, you have to partition them into clusters C1 to CK. This partition has to minimize the collective distance, sum of the distances between each point and the corresponding centroid. Now, the centroid is defined as the center of mass of each of the clusters, and this problem is famous and significant because it gave rise to this particular algorithm, which is well known. It's called k-means. In fact, probably the algorithm came before the official definition of the problem. So k-means is actually a heuristic algorithm. It starts with a given initial clustering, and then it improves it iteratively by alternating the computation of the centroids, and then based on these centroids, it re-evaluates the distances between the centroids, the new centroids, and all the points. And then based on those distances, it reassigns the points, certain points, to centroids that make more sense. And then this is repeated until stability. So the complexity of the problem is NP hard. The reduction is from densest cut on the complement graph. There are a bunch of approximation algorithms that work in polynomial time, but they all make assumptions. For example, some of the parameters of the problem have to be fixed. The approximation algorithm for general K and N, so general number of clusters and number of points, is actually not very helpful at 9 plus epsilon. There's also a result that says that this 9 cannot be made any smaller. The problem itself is also NP hard to approximate to within a factor 1 plus epsilon, but the proof holds for very small values of epsilon, and we don't know whether this proof can be improved to cover larger values. So I mentioned the site constraints. The site constraints, it means that you want to add some technical constraints. Now, this is something that happens very often with abstract problems. You get an abstract problem such as maximum flow, and it's all very good and dandy, but then you want to do something with it, and then there are some other constraints creeping in from reality. I don't know, you might have some weird rules for enforcing capacities on cables and so on and so forth. So many of these algorithms, constraints usually ruin efficient algorithms that assume that a certain structure is always going to be there and unchanged. So k-means, for example, does not allow for extra constraints, but there are some versions of k-means that do allow for some types of extra constraints. For example, the must link or cannot link, some delta constraints and epsilon constraints, and some other specific constraints. For example, you can add one quadratic constraint and still run k-means. Different versions of k-means. You have to adapt k-means to all of these constraints. But if you don't know in advance what kind of constraints you will have, then this is much more difficult. I mean, adapting k-means needs a structure. If you don't know what the structure is going to be, it's going to be difficult to adapt k-means. So, for example, constraint programming has made an objective of this task to adapt, to derive a constraint programming formulation for the k-means problem, not anymore the algorithm, but the problem, so the MSSC, with general constraints. And by general, CP is pretty general in the sense that you can have many constraints in constraint programming that really difficult to enforce in mathematical programming. On the other hand, each time you want to generate a new constraint in constraint programming, you have, to add a new constraint to constraint programming, you have to code, you have to implement a filtering algorithm and perhaps some other types of algorithms like bounding algorithms and new constraint programming solvers, some other types of algorithms, and you have to put them into the constraint programming solver. So it's not as complicated as adapting k-means to any unstructured constraint or any new constraint that might come along, but it's still difficult. You have to still, get down and work. The advantage with mathematical programming is that you just need a new model. So you implement the new constraints inside of the mathematical programming formulation, and that's about it. Then you just call your solver. So this work contributes some formulations for the k-means problem, so the MSSC problem, in presence of general convex MINLP constraints. So let's look at some formulations. The MINLP formulation, the natural one, is given in this slide here. It doesn't do anything bizarre. It introduces some binary variables x, okay, that choose whether you sum up these distances to the general sum or not. And the choice is based on whether point I is assigned to centroid j. Okay, so this is actually the meaning of these binary variables. Then you have the definition of a centroid. These y's are vectors, so yj is itself a vector in Rm. 1 over Sij, that would be the Sij would be an integer variable that denotes the cardinality of the cluster. So this is really the definition of the center of mass and nothing more. And finally, this is the partitioning constraint that says that each point has to be assigned to exactly one cluster. Okay, so this is a complicated MINLP that has continuous variables, and it has binary variables, and it has also possibly unconstrained general integer variables. Okay, so you really don't want to throw this formulation at any solver, be that as it may. It's way too complicated for any reasonable solver. But there are very easy reformulations that we can do. For example, by optimality, we can simply replace the complicated term, the norm term in the objective function, in the product. In this product, we can replace it by a single additional variable, Pij. Okay, so this Pij now becomes an upper bound to a constraint that ends up defining a convex region in space. Okay, so this already gets rid of some of the non-convexity in the previous formulation. Now we still have to deal with two products of variables, this one and this one, but both are continuous variables by binary variables, and we can assume that the continuous variables are bounded because of these constraints, meaning that you know that the centroid has to be reasonably close to the points, and in fact it has to be inside a hyperrectangle defined by the points given as an input of the problem. So there's no problem to bound the y variables, and similarly you can bound the p variables. So everybody knows, or should know here in this audience, that variable products of binary variables times continuous bounded variables can be linearized exactly. And so this is what we're doing in this slide. And this is finally a convex MINLP formulation of the MSSC. It has a few sets of additional continuous variables here. But on the whole, it works quite well. Now, one thing you might want to do is to consider whether the 2 norm, which is complicated in the sense that it may be a convex term if used carefully, but it's still non-linear, whether this norm could be replaced by the 1 norm or infinite norm that are known as linearizable norms, because in mathematical programming you can linearize them. So you can replace the L2 norm terms with L infinity by and then you can simply add these constraints to the formulation, which define the enforcement of the L infinity norm between P and the centroid. Okay. Similarly with this is L infinity, this is L1. Similarly with L1, you can replace L1 in this way, where you can recognize the reformulation of the absolute values, and then this is the sum of all of the absolute values of the terms, and these are the 2 constraints that you need to replace the one norm width. And because we know that there are norm inequalities that everybody knows about, we can quickly derive some approximation guarantees on the values of the optima of the MILPs that these replacements afford. Unfortunately, these approximation guarantees are not very good. You can see 1 over m and m in the extreme terms, which mean that they are only useful where m is small. So, for example, in the plane, not in the place, but in the plane. So this is where random projections come in. The gist of random projections is that they can transform very tall matrices into very fat but very short ones. Here you see the blue matrix A. This is your data matrix. I'm calling it A for generality, but in fact this would be what we called P in the formulations, or rather the matrix P consisting of all of the points Pi. Okay, so this would be our target matrix, but let's call it A right here. And T, well, and this matrix T that preconditions A is a shortened fat D times M normally sampled component-wise matrix, so that the end product T times A is such that every row is a random aggregation of all of the other rows. Okay, but point is that here you have n columns and m rows, whereas here you have n columns and only d rows. Okay, so d is supposed to be much smaller than m, and in fact we'll see in the next slide how much smaller it will be. Anyway, if you do this, you will obtain a set of points, projected points Ta, that are almost congruent with the points in A. So the columns of A, you can see here, the two norms of the columns of A are approximately the same as the two norms of the differences of columns of Ta. Okay, this happens WAP. I'll say later what WAP means. So anyway, so it happens WAP, and this means that WAP, a smaller size of your problem, means that any algorithm for the solution of your problem will solve it faster. All right, so what does WAP mean? WAP means with arbitrarily high probability, and it describes a sequence of events ED, depending on some parameter D, that approaches 1 exponentially fast and as D increases. So you would have here the probability of ED is more or less like 1 over 1 minus this falling exponential of D. Okay, so this means that the probability of the event holding WAP approaches 1 exponentially fast. So this is the slide where I explain what D is, okay, with respect to M. The Johnson-Lindenstrauss Lemma is probably the best known result to do with random projections. So given this set of points A, or matrix A, with n points, the columns of A, and a given epsilon, then there is this integer D, which is more or less like a logarithm of n over epsilon squared. Now, epsilon squared is going to be large because epsilon, you want epsilon small. So 1 over epsilon squared is going to be large, sorry. And then the logarithm of n is going to be small with respect to n, okay? So if you pretend that you're fixing epsilon, this is like D being logarithm of n. So whatever m was, if it wasn't too different from n, then D is going to be much, much smaller. So D is really going to be much smaller than m. Okay, in general, this is the usefulness of the Johnson-Lindenstrauss Lemma. Now, the proof is probabilistic, and the matrix T is sampled component-wise from this normal distribution centered at 0 with mean 0 and with standard deviation 1 over square root of D. So A and TA are approximately congruent with a small probability. That's what the proof does, which means that the result will follow by the probabilistic method. In practice, A and TA are approximately congruent with probability 1 over n, which is enough to give you any high probability you might want by resampling sufficiently many times. Not very many times, in fact. But empirically, you can sample t very few times indeed. For example, I just sampled them once, okay? Because there's a result that says that the average of the differences, the distances between projected vectors is going to be the same as the average of the distances between vectors, okay? So the probability of error decreases exponentially fast by the Johnson-Lindenstrauss Lemma, which means that in practice, maybe you will, even if not all of these pairs will yield the result of almost congruence that you see here up to epsilon, in fact, very few pairs will deviate from that. And if you have huge matrices, a few deviations, the chances are the matrices are not going to be precise anyway. The data will come from some source, and if you have huge amounts of data, some entry will be wrong anyway. So what does it even mean to say, a few things will be wrong in my algorithm? So maybe you're deviating from the truth already in the data. The surprising fact is that D is actually independent of the original number of dimensions M and only depends on epsilon and the number of points. Now, projecting points is one thing, but projecting formulation is quite another. So of course, we project the data in the formulation. So in that sense, we are projecting kind of points. But you also want the solutions to be projected. So somehow, projected consistently with the data. And so somehow we want the decision variable domain to be projected as well, which poses some issues because if the domain of the variables, for example, is infinite, well, there's a problem there because here we're assuming that the matrix T works for sets that are finite, okay? So this is one difficulty. And the other difficulty is that approximate congruence and approximate optimality are two different things. I've worked on this topic for a number of years now. So we've done LPs, SDPs recently, and conic problems. We've done QPs, even on convex one, or QPs over a ball, and now we're dealing with a single problem. Now, notice that these were all problem categories, so this was very general. All the previous work was very general. This is a single problem, okay? So it's a class of instances. So it's not as general, but there are integer variables here, so it's the first time that we can manage to deal with integer variables. So we're quite happy about that. Let's see how random projections apply to the MSSC. Sorry. In fact, there's another paper, Boutsidis and other people, a paper that came out at NIPS 2006 that consider a different formulation of the MSSC and applies random projections to it. You can see here the minimization of the data matrix minus the centroid matrix. So this centroid matrix, we're going to see later that this is a low rank matrix, okay? Anyway, so the variables are the centroid matrix, of course, and these matrices in this set calligraphic X. And this constraint here is really the definition of the centroid. So if you compare it to the formulations that we had, okay, so this, okay, that constraint there in Boutsidis formulation was really a version of that, okay? Why? Well, because these calligraphic X here is the domain of these cluster indicator matrices. These are not quite binary matrices, well, meaning that the variables inside the matrices are not necessarily binary variables, but they are almost like that binary. They behave like binary variables multiplied by a scalar. So in fact, if we write x equal x bar ij, then the point pi is in the cluster cj if and only if bar xij is 1 over square root of the cardinality of the cluster, or 0 otherwise, okay? So these matrices are sort of matrices of binary variables, but they're not binary. They're either 0 or a non-zero, which is this one here, okay? And this lifted centroid matrix, because of this definition and because X, these matrices are n times k, so n times k times n. This is an n times n matrix. This is an n times m matrix, but this is going to be then a rank k matrix, okay? So we replace y here by its definition, and we obtain this unconstrained reformulation on just the x variables. So now we can simply replace P transpose by PT transpose, okay? So we replace the point matrix P by TP. And any algorithm that solves MSSC will simply see after this replacement of data matrices with projected data matrices another smaller instance of the MSSC problem. So any algorithm that solves the MSSC applied to the projected problem, well, Boutsidis and I'll show that provides a 2 plus epsilon approximation algorithm. Okay, so if your MSSC algorithm guarantees the optimum, then after you project the matrices, you will find a 2 plus epsilon approximation on the optimum. All right, so some of the proof details are as follows. So by the JLL, D is actually proportional to logarithm of n, the number of points, okay? But in Boutsidis and all, it turns out that D is proportional to the number of clusters, which is much, much smaller than the number of points. So this is actually very, very interesting and also somewhat unbelievable from my point of view. Anyway, so the proof is built on this other paper, came out in Fox 2006 by Sarlos. And the crucial lemma 2 by Boutsidis and al. Mentions this bound where sigma j is the jth singular value and uk is the left singular vector matrix of the point matrix P. The results in Sarlo's paper proving star states that D is in fact this quantity, okay, which is correct. But unfortunately, in Sarlo's paper, k, the symbol k, actually points to the number of points n. So in fact, this is really what Sarlos is proving in our terminology and also in Boutsidis' terminology. So if we really want to say that Boutsidis did not overlook this detail, but simply made an inference, then you have to equate the D in Boutsidis' paper to D in Sarlo's paper. And then you obtain either of these two possibilities, this or that. But neither case, if you think about it, neither case can hold. So perhaps Boutsidis' proof is broken. Now, we couldn't fix Boutsidis' proof in any way. And then we think that there is a fundamental issue about Boutsidis' proof. It builds on Sarlos, as I said, and Sarlos builds on the JLL. But the JLL only holds for finite sets of vectors, whereas the number of possible centroids, and here in this problem we are projecting the centroid variables as well, meaning that after projecting the data, we want the centroids also to be consistent with the projected data. So we expect the T matrix also to project some variables, some decision variables, okay? So let's look at the domains of these variables. The number of possible centroids, there are as many possible centroids, positions, as the partitions of endpoints in k clusters, okay? So the decision variables of the MSSC formulation can take up to this number of values, okay? So they are finitely many values, so random projections do apply to finite sets, okay? But the number of the projected dimensions is proportional to the logarithm of the cardinality of these sets now, okay? So this Bn is called Bell number, and we know that the logarithm of Bn asymptotically is like log n, okay? So actually we get D, which is n log n over epsilon squared, which is only useful when n number of points is much, much smaller than the number of features of the points, which is not a general case. So it seems unlikely that Boutsidis and al. Might have proven this result in whole generality based on the JLL. Now Sarlos proves something different. It doesn't really go into NP-hard problems in his papers. So there may be a fine line between what Sarlos is doing legally and correctly, as far as we can tell, and the fact that Boutsidis and al. Has this. In our opinion, there's a proof that doesn't quite work, or we don't understand why it works, at least. Anyway, so we provided a new proof where we use the additive JLL instead. You can see that instead of having 1 minus epsilon and then 1 plus epsilon as the JLL, we have minus delta and plus delta here. So it's an additive version. Its advantage is that it works with infinite sets S, okay? So now we can actually retrace the steps of Sarlo's proof and Boutsidis proof and get to the end in a convincing, correct way. We obtain different bounds that are worse than Boutsidis and all, but we managed to prove this theorem that I'll let you parse in your own time. So the computational results, let me just say something. This fundamental issue that we think we found with Boutsidis proof might seem to be negated by the fact that Boutsidis papers have computational results supporting the theory. On the other hand, JLL-related theory enforces bounds which may be slack in many cases, even though they need to be high to cover every possible case, every possible instance. In many classes of instances, maybe they are slack. And so maybe the tests do succeed even if the theory is not quite correct. So we've found that ourselves in investigating random projections with other problems. So anyway, our computational results are performed by simply solving convex MINLPs, which are quadratic in this case, and MILPs with Cplex on a bunch of instances. We can only run Cplex determination for very, very small instances, so that's not a good sign, unfortunately, but that's what we found. The validation was good, meaning that similar results on P and TP were found, but TP was faster, so that's all good and according to what we were expecting. And it does also give a flair for usefulness for what we found. And we can find good optima on side constraint instances from the UCI database, which is very good. Unfortunately, we can't compare with the constraint programming approach, not really because of the difference I sketched earlier between how you have to implement in CP, whereas you just have to add to the formulation in MP, but because this paper actually uses instances with very, very few features. And of course, we can't project few features if they're already few. So we are forced to test our methods on a different set of instances, and we couldn't really... So in this paper, the authors give instructions as to how they set up their method, and it appears to be possible to replicate those things, but the solvers... the CP solvers they use, I tried to install it, I tried to run it, and I couldn't. So at least we can't compare for technological reasons, let's say. Okay, and this is the end of my talk. Thank you very much.